With this video, we begin Chapter 4, our unit on the electronic structure of the atom. We finished our previous unit with Rutherford's nuclear model of the atom. In the nuclear model of the atom, you'll recall that all of the positive charge and nearly all of the mass is located in a small, dense region at the very center called the nucleus. It contains protons and neutrons. The atom is identified by the number of protons, called the atomic number, whereas the mass number is the sum of the protons and neutrons. The electrons exist around the nucleus in what is vaguely defined as the electron cloud. Okay, but what exactly are the electrons in the atom doing? I will answer that question below, but first we have to talk about a couple of different things. We have to consider the nature of electromagnetic radiation. We have to look at what's called the emission spectrum of hydrogen. We have to consider the Bohr model of the hydrogen atom, which will finally lead to the quantum mechanical model of the hydrogen atom, which answers the question: the electrons occupy atomic orbitals as described by the atom's electron configuration. Let's first talk about electromagnetic radiation. What is electromagnetic radiation? Electromagnetic radiation is a form of energy that has wave-like properties as it travels through space. It is made up of electric and magnetic field components that oscillate in phase perpendicular to each other, but you really don't need to know that. But you do need to know that all forms of electromagnetic radiation make up what's called the electromagnetic spectrum. And every physical science textbook ever published has a diagram like this. It shows on a spectrum different types of radiation. Radio waves, infrared, visible light actually accounts for a very small portion of the electromagnetic spectrum, ultraviolet, X-rays, and gamma rays. And notice along the top there is a scale that has units of distance. Wonder what that refers to. Well, every wave has certain properties. Wavelength, symbolized by the lowercase Greek letter lambda, which is the distance between crests on adjacent waves. A wave is also characterized by the frequency, which is the number of waves or peaks that pass a given point in a given period of time. And that is measured in cycles per second, for which the unit is 1/seconds, which is also sometimes replaced with hertz, but you can simply use 1/seconds. So the question is, how are wavelength and frequency related to each other? As you can see in these two diagrams, as the distance between adjacent peaks gets smaller, that is, as lambda decreases, the number of peaks that pass you in a given second, that is the frequency or nu, increases. So as the wavelength decreases, the frequency increases. And you remember from our first unit that if two variables are related such that as one gets smaller, the other gets larger, that means they are inversely proportional. And you will further recall that if two variables, in this case lambda, which represents wavelength, and nu, which represents frequency, are inversely proportional, they multiply together to give a constant. That constant is the speed of the wave, and in the case of electromagnetic radiation, that has a value of 2.998 times 10 to the 8th meters per second. So let's see how we can use this equation to interconvert between the wavelength and frequency of different forms of electromagnetic radiation. Calculate the frequency in hertz or reciprocal seconds of infrared radiation that has a wavelength of 1,225 nanometers. Well, I'll begin by writing out the equation. Lambda times nu equals c, or wavelength times frequency equals speed. I'll divide both sides by wavelength, cancel wavelength on the left, and I obtain my rearranged equation. Nu, or frequency, equals c over lambda, speed over wavelength. I'll plug in my values with the correct units. Meters in the numerator cancels meters in the denominator, and I'm left with a value of 2.447 times 10 to the 14th. The unit, pay attention, is not seconds, it is 1/seconds, which is the correct unit of frequency. By the way, you'll see I simply, instead of doing a separate conversion of nanometers to meters, using the fact that nano means 10 to the negative 9th, I simply replaced the n in nanometers with the corresponding power of 10. So it's perfectly acceptable to express 1,225 nanometers as 1,225 times 10 to the negative 9th meters. Let's do another example. Here I give you X-rays with a frequency of 5.27 times 10 to the 17th hertz, or reciprocal seconds, and I want to calculate the wavelength in picometers. I will rearrange my equation now to obtain lambda, wavelength, equals c, the speed, over nu, the frequency. I plug in the speed of electromagnetic radiation in the numerator. I plug in the specified frequency, 5.27 times 10 to the 17th reciprocal seconds. I obtain a value of 5.69 times 10 to the negative 10th meters. Notice that seconds in the numerator, the denominator of the numerator cancels seconds in the denominator of the denominator, leaving me with meters, which is the unit I expect for wavelength. However, the question asks for this in picometers. Pico means 10 to the negative 12th, so I'll take the wavelength I calculated in the first part of the problem, multiply by 1 picometer over 10 to the negative 12th meters, and I obtain a wavelength for this X-ray of 569 picometers. Now, at this point, in the late 19th century, everything was fine and dandy. Everyone simply believed that electromagnetic radiation is just a wave-like phenomenon, and that's all there is to it. However, experiments described in the textbook, which you can look at if you want, show that electromagnetic radiation is not just wave-like. Einstein showed that electromagnetic radiation has both wave-like and particle-like properties. It's wave-like when it's traveling through space, but it's particle-like when it is being absorbed by or emitted from atoms. Okay? This is called the wave-particle duality of electromagnetic radiation. And when energy is being particle-like, we say that it is quantized. What does that word quantized mean? We'll be using that a lot this unit, so let's make sure we understand it. With reference to energy, it means that energy is absorbed or emitted by an atom one chunk at a time. When an atom is gaining energy from an external source or giving off energy, it does not do so freely like water flowing from a faucet. It does so one piece of energy at a time. Our name for the particle of electromagnetic radiation is the photon. The amount of energy contained in one photon, which is the minimum amount of energy gained or lost by an atom, is called a quantum of energy. And Einstein showed that the energy contained in a photon is directly proportional to the frequency. The equation we use, E representing energy, is equal to h, a constant, times nu, the frequency. H is called Planck's constant, which has a value of 6.626 times 10 to the negative 34th joule seconds. Nu is the frequency in units of reciprocal seconds. So let's do some calculations in which we interconvert between energy, wavelength, and frequency of electromagnetic radiation. How much energy is contained in 1 photon of UV light with a wavelength of 50.0 nanometers? How much energy is contained in 1 mole of these photons? Well, I'll begin by writing my equation. Energy equals Planck's constant times frequency. We're not given the frequency, we're given the wavelength. We could do a separate calculation as we did before and convert from wavelength to frequency, but instead, why don't we simply do an algebraic substitution and in place of frequency in the first equation, simply plug in c over lambda, or speed over wavelength. That gives us our rearranged equation, energy equals Planck's constant times speed divided by wavelength. I'll plug in my numerical values for Planck's constant and the speed of electromagnetic radiation in the numerator. I will divide that by 50.0 times 10 to the negative 9th meters, again expressing nanometers as simply 10 to the negative 9th meters. You'll see that seconds cancel in the numerator, meters in the numerator, cancel meters in the denominator. That leaves me with a value of 3.97 times 10 to the negative 18th joules, which I'll express as joules per photon because we're dealing with a single photon. The question further asks, how much energy is in 1 mole of these photons? Well, how many photons are in a mole? How many of anything is in a mole? Of course, Avogadro's number. So to convert from joules per photon to joules per mole, I'll simply multiply the energy calculated in the first part by Avogadro's number of photons per mole to give me a value of 2.39 times 10 to the 6th joules per mole, which is a lot of energy. In our final problem, I ask the question, a photon of electromagnetic radiation contains 9.93 times 10 to the negative 26th joules of energy. What type of radiation is it? How are we going to identify the type of radiation? Well, we have, from the previous problem, energy equals Planck's constant times speed divided by wavelength. I'll simply rearrange this algebraically to isolate wavelength. That gives me wavelength equals Planck's constant times speed over energy, or lambda equals hc over E. Again, I'll plug in my values for Planck's constant and speed, plug in energy in the denominator. Seconds cancel seconds in the numerator, joules in the numerator cancel joules in the denominator. That leaves me with meters. That wavelength is 2.00 meters. How do I identify it? Well, I simply go back to my electromagnetic spectrum and I see that waves with wavelengths on the order of a meter are radio waves. So I'll answer the question by saying these are radio waves. In our next video, we will talk about the emission spectrum of hydrogen and what it means about energy levels in the hydrogen atom.